So I'll proceed with the presentation. So distinguished guests, esteemed colleagues, and fellow researchers, it is with great honor and enthusiasm that we present our work, analysis, and advancements in domain-specific template question answer. The pivotal topic has garnered significant traction recently due to burgeoning of its use in AI agents for query answer. Our approach aims to refine the methodology for question framing, thereby enabling large language model or LLMs to comprehend the query more effectively and provide superior responses. Our research emerges as a solution in the corporate landscape, where substantial time and financial resources are invested in training new employees. The subsequent visual representations uh, The subsequent visual representations vividly illustrate the challenges corporations face and the profound impact our agents can have, significantly optimizing resource allocation. To, to illustrate the pressing need, industry studies reveal some concerning statistics. Nearly 60% of the support tickets necessitate routing across multiple internal teams for resolution. Perhaps more alarmingly, over 70% of the employees' time is spent on communication rather than core work duties. Our compositional methodology directly addresses these inefficiencies, significantly reducing the issue resolution time over by 40%. When deployed at a scale across an enterprise, this translates millions of dollars in annual cost savings derived from optimized employee productivity. So, as you can see, this is one of the examples of what our solution does. Usually, you would need an expert in SQL to perform SQL queries for database search and operations. But with our provided solution, you can simply use natural language or simple, you plain English to to finally result in the same task. This speeds up the corporate workforce, which in turn has the potential to yield substantial financial returns or savings for that matter. Moving ahead, and pursued in this direction, we initially engaged with one of the leading large language models, which is GPT-4. So, utilizing a monolithic prompt to extract desired set of tools and their corresponding argument values. As we have already demonstrated that, as we have already said that we'll be providing a solution, demonstration via tool retrieval. So, yeah, coming to the GPT-4 cheat code or how GPT-4 alone can solve everything in one go, and how this solution needs to be optimized. Utilizing a monolithic prompt to extract the desired set of tools and their corresponding argument values. As anticipated, GPT-4 demonstrated a commendable performance. However, grappling with the high inference API cost. As we can see, the average latency remained to be 11.9 seconds, which is huge, and average per query cost remained to be $0.02. We can just scale it up to understand how much this becomes. So let's say 1,000 queries per second translates to $20 per second, and that is a huge cost that needs to be optimized in a great manner. Moving forward with our solution, so optimization gave us a direction. We provided GPT-4 with a JSON schema outlining the available toolset, then issued the API calls to solicit output responses tailored to each user query. Results were quite promising, with the GPT-4 excelling in zero-shot prompting and demonstrating excellent performances when provided with a all-encompassing necessary information. However, despite its progress, as already mentioned, high computational demands posed obstacles. Transitioning to the pragmatic choice, GPT 3.5, we navigated to subtle differences between the two models. So, the subtle differences between the two models are listed here. And notably, when confronted with the complicated task, a discernible performance distinction emerged. This contrast is visually encapsulated in the accompanying graphical representation, which is the provided one. Now, as we delve into the intricacies of our approach, the promising outcomes will be heralded. Allow me to walk you through the experiments that we concerned, commencing with distillation. So, as we already mentioned, this is the path that we took. The It started with reducing cost. It reached to prompting. And our final solution will include GPT 3.5 API calls plus chain of thought prompting in a manner which is very different from the pre-existing ones. So, conducted experiments started with distillation. Now, distillation in machine learning terms is making one model learned by another larger model. That is distilling the information from one huge model, which has, let's say, millions of parameters, to a model which is specialized in some task, which is a subset of the larger model. So, the findings of distillation step by step paper are very promising, particularly when dealing with the smaller training data sets and models. Our curated dataset comprising a mere 6,000 data points generated through GPT-4 with the chain of thought prompt, features queries, output toolsets, and accompanying rationales. Leveraging this dataset, we distilled the Google T5 large language model, and we had different types of distillation in place. One of them was multitask learning, and the other was single joint task prediction. So these are the differences mentioned between the two, and this is what we perform. So, despite the challenge of overfitting due to its modest size, the distilled model demonstrated significant performance improvement, underscoring the viability of our distillation step by step approach. With a more extensive data set, in tandem with our cost optimization endeavors, we focused on enhancing process explainability by venturing into a more interpretable domain, the embedding space. Our devised approach resolved around an asymmetric query and tool similarity metric. Before delving into the intricacies of this methodology, allow me to familiarize you with some foundation terms. Here are a few key terms that will be frequently used in our next experiment. Vector span. We will utilize vector embeddings of tool and query. The tool and query embeddings may not necessarily lie in the same vector space. This may lead to incorrect similarity scores. Thus, we take the vector span of a tool embedding and project the query embedding onto the span. All vectors are now in the same space, ensuing consistent similarity scores and allowing for absolute thresholding when constructing tools or query trees. This is essential for the method that follows. Now, we use the sentence bird to leverage building vector embeddings. Our tool queries, the sentence bird, what it does is takes the tool descriptions and the query descriptions and converts it into embedding space, which is something that exists already. This is not something new that we have come up on our own. Now, coming to the workflow, FICE indexing, that is Facebook AI similarity search, is often used for efficient similarity search and KNN retrieval, and that is what we use. After conversion to SBERT and vector span, a simple query fetch, that is similarity score fetch, returns top K tools, which is the tools that we are going to use in the demonstration of our solution. So, search. One of the indexes built, we perform similarity searches. Given a query vector, FAST efficiently retrieves the dataset vectors most similar to the query vector. Parameter K. The parameter K is the number of nearest neighbors to be returned. As you can see, top K tools are returned. And when we search using FAST, we specify how many neighbors we want to retrieve for each query vector. Returning to the LLM, having seen GPT-5, GPT 3.5's inherent capabilities, we tried to retrieve for each query vector. We tried to incorporate various prompting techniques to improve the performance. Established prompting methods such as chain of thought prompting and tree of thought prompting showed only incremental and enhanced improvement, respectively, in the fidelity of outputs and their correctness. It was an improvement nonetheless. Therefore, we devised a tweaked version of chain of thought that we'd like to call sequential COT. First, I would like to explain chain of thought or standard chain of thought in a single prompt requiring the LLM to reason in steps. So, as you can see, this is GPT 3.5 plus tree of thought. Tree of thought maintains a problem solving tree with coherent language sequences for guidance. And GPT 3.5 plus COT, chain of thought sequentially linked prompts to guide the conversation for natural flow in the internal monologue of the large language model. Now, this is how 3.5 works. You give a prompt and it returns you a direct solution. But in the chain of thought, you give a prompt and you ask the model to think step by step, which is one of the most prominent ways of chain of thought prompting to exist. Now, the solution returns with a reasoning as an internal monologue of the LLM itself, which makes the result even more enhanced, enriched, and better. So our solution, AOT or a sequential of thoughts. You can also call it array of thoughts. It has iterative interaction sequence, unfolding dialogue through a series of user-assistant interactions. It ensures a nuanced understanding of evolving context. It has comprehensive response generation. Assistant analyzes the entirety of the conversation history and context-driven responses, which has enhanced coherence and relevance. Here, the representative flow is as follows. As the user enters the query, it is changed with the system prompt. It is chained with the system prompt to return a response. The system prompt gives element identity to start with. It further defines the task, its requirements and output scheme. This stage also requires the LLM to identify the tools that would be used to solve the query. The output is then sent as user input, along with the assistant prompt instructing GPT to sequence tools correctly. Once we have the sequence of required tools, the following prompt has instructions for filling in argument names and values for the respective tools and referencing previous argument values if necessary. We now have the output in an unstructured fashion. Hence, the last prompt assists in aligning the response with the required output scheme. Now, let me illustrate the high level flow with the history implementation. So this is how it works. We have just shown how sequential COT works for an individual query. This flowchart illustrates how our method works for multiple queries in a conversational setting. We maintain a history log comprising the agent prompt, the user query, and the corresponding output. The query and the log are taken as inputs every subsequent query. The sequential COT methods act upon this input and returns an updated log with the current output. The log is maintained, and as long as the current session is active, thus ensuring the context is preserved throughout the conversation, enabling the LLM to provide more coherent and contextually relevant responses. Now, looking at the key takeaways from our approach, an appropriate prompting method, which in this case was sequential COT, plays a crucial role in the LLM's performance. With this method, we could bring GPT 3.5 capabilities within appreciable margins of GPT-4, while inference costs remained lower. Multiple GPT model, GPT slash model, commonly known as the mixture of expert approaches, is another avenue we explore. Allow me to present a simple scenario with two models. Uh, you can have two different models to solve the same query in a fast and other model in a slow manner, which would finally result in two approaches to a single solution. This is something that is a key takeaway from the paper thinking fast and slow. What this does is this enhances the output value as we are taking two different pathways to reach the same solution, and enforcing them to reach the same solution results in a more enriched internal workflow or rationale that is obtained. It is not something that we have used in our solution, but it lies in our future scope. Now, future scope outputs are not solely based on the tool set, but they are more domain aware. As we already said, this is just a demonstrative example. Restricted tool access. Now, restricted tool access follows that we can have, since ours is a user and client interactive solution, we can always have restricted access if for different levels of corporate employees when going into the practicalities of its implementation. We can have improved distillation with a larger data set, since our data set only comprised of 6,000 in-house generated points and multiple GPT client or mixture of expert approaches as mentioned in the previous slide. So this is the video of how our tool works. So as you can see, this is the tool set, and we have provided queries of different tools here. I'm so sorry. We have provided descriptions of different tools here with their relevant arguments. So this is the tool set. Now you can just go into the chart and you can say hello. So the response is none, as this particular thing is domain aware. This realizes that its task is tool retrieval. Now, if we ask a more relevant question, what will it do? You will see further in the video. Now, the question is prioritize my P0 issues, and the response generated is as follows. So, as prior mentioned, our latency rise in the range of 11.9 seconds. So this is the response generated. So it retrieves the array, it retrieves the object, the tool name, and everything is given. So this is how our solution is leveraged for tool retrieval. And thank you for your esteemed presence and attention. We look forward to engaging with you and addressing any queries or insights that you may have. This was it for our presentation.